In this video, we will discuss about artificial neural networks. Neural networks are a class of machine learning algorithms used to perform machine learning tasks like classification, regression, clustering, etc. We can work with neural networks in both supervised and unsupervised settings, which means that neural networks can work with labels and also without labels. Under supervised settings, neural networks are a similar and extension to logistic regression. In logistic regression, we have a single artificial neuron with inputs connected to the weights, and we learn model parameters during the training, and during the testing we try to predict the probability of an input belonging to a particular class. In the same way, in artificial neural networks, we try to do the similar task where we try to learn the model parameters, and during the testing stage we try to predict the probability of an input belonging to a particular class. The important difference is in logistic regression we do only binary classification, whereas in neural networks, as it is very general, it can do multi-level classification. And also the nonlinearity between input and output is harder in logistic regression, whereas in neural networks, as there are multiple artificial neurons, any sort of non-linearity between input and output pairs can be learned during the training stage, and later during the testing stage for any input it can classify into one of the classes. In the last layer we will be getting the probabilities as an output, just like in logistic regression. So we will try to see all these details in this video. So consider x1, x2 and so on, xn naught are the inputs. So these inputs, when multiplied with the weights and added with a bias, we get a pre-activation. As you can see here, this superscript indicates that it belongs to the layer 1, and the subscript indicates that this is the pre-activation of the neuron 1. So, and the weight have the superscript indicates the layer, and the subscript indicates, the first subscript indicates that it is going to the neuron 1, whereas the second subscript indicates that it is coming from the neuron 1. For example, if you take for the second neuron, we will call this as W21, which means that 2 indicates that it is going to the neuron and 1 indicates that it is coming from the input x1. So in this way we compute the pre-activations z1, z2 and so on, zn1 for the first layer, and this passes through an activation function. Here we have listed sigmoid as an activation function, but there are other activation functions. So one of the prominent one is the ReLU activation function. We can use various nonlinear activation functions to learn the nonlinear relation between input and output. So once we get the post activations A1, A2 and so on, AN1, these post activations acts like an input to the next layer of next layer. So here we take these post activations as the input and multiply with the second layer of weights to obtain the pre-activations of the second layer. And in the same way we do it for all the neurons in the second layer, and we can have arbitrary number of neural units in each layer. As you can see here, we have n1 units in the first layer and n2 units in the second layer. Once again, these units also have a post activation which is indicated using A1, A2 and so on, AN2, where this 2 superscript indicates that these belong to the layer 2. In this way we go on, it goes on until it reaches to the last stage where we have lth layers pre-activation, which passes through an other activation function, which is usually when we do a multi-level classification we use softmax as an activation function, because it gives probabilities when there are more than 2 classes. In logistic regression, if you see, we use sigmoid activation function because it gives probability as the output. But since there are multiple classes, we use softmax as an activation function for neural networks. So important thing to remember is this is the supervised way of learning model parameters in neural networks, whereas we also have neural networks can also be used under unsupervised setting also. That is discussed in another video. So let us, once we get the outputs of the final layer, which are the post activations of these softmax functions, these are the probabilities y1 cap, y2 cap, and so on, ynl. These probabilities indicate the input belonging to a particular class. So whichever class has the highest probability, we say that the input belong to so and so class. So in order for the neural network to successfully determine which class a particular input belongs to, first this neural network has to get trained. So in the beginning, we will not have any proper trained weights. We will randomly initialize the weight, and we do what is called as forward and backward propagation using an algorithm called as backpropagation algorithm, and obtain the optimal weights for the neural networks during the training stage. During the testing stage, we use these optimal model parameters which we got and also the test input to obtain the probabilities and thereby determine which input class, which class the test input belongs to. So this is what we do. We use once again the same cross entropy as the loss function for neural networks. We use the same idea of chain rules to obtain the partial derivatives and thereby obtain the gradients for the update equations of the weights. So we compute these gradients dou L by dou W Jk for every layer. So this is for the lth layer. If you want for the other intermediate layers, so I-1's layer gradients depends upon the ith layer gradients. So as you can see here, so this is the pre-activations of the ith layer. This is the post-activation of the previous layer. As we know, I-1th layer act like an input. I-1th layer's post activations act like an input to the ith layer pre-activation. So we establish the relation and we compute these partial derivatives and thereby obtain these gradients and thereby update the weights in the backpropagation algorithm. We are not going to derive the complete derivation here. We have seen the logistic regression complete derivation, whereas here we will be utilizing these ideas, and I will be mentioning the final update equations, final gradients and final update equations, and later we will see one problem on it. So let us, this is the general neural network with arbitrary number of layers and arbitrary number of units in each layer, and arbitrary or the a standard activation functions for the hidden layer and an activation function for the final layer. So now let us take these are the other activation functions which are available. We have linear, sigmoid, tanh, and ReLU. ReLU is one of the famous activation function used in the hidden layers, and all of these activation functions attempt to, these three activation functions attempt to learn the non-linearity between input and output, whereas linear activation, which is only used under the cases where there is a linear relation between them. So we have softmax activation function, which is usually used in the final layer whenever we want to do multi-level classification. So this is the activation functions equation where we get the probabilities, where we get the values between 0 and 1, and these act like a probabilities for an input belonging to a particular class. So let us now see, take a smaller case of 2 cross 2 cross 2, where 2 inputs and 1 hidden layer and 1 output layer, and see how the propagation happens, forward and back propagation, and also we'll derive the update equations. We'll actually see the update equations rather than completely deriving it. So as we know, these are the inputs. We will be having the pre-activation Z1 and Z2, Z11 and Z12, which are where we multiply weights with the inputs and add with the bias and we obtain it. When we represent in the form of matrix, it looks something like this, where W1 is the weights of the first layer and B1 are the biases of the first layer. Once we pass through the activation function, we get the post activations, and these post activations act like an input for the next layer, and we obtain the pre-activations of the next layer. The same idea which we saw for the general case is simplified here for a 2 cross 2 cross 2. So once we obtain the pre-activations, we pass through the activation functions and we obtain the final post activations, and these post activations y1 cap and y2 cap are the probabilities, and we try to compare these with the actual values which are y1 and y2 and obtain the error through the cross entropy loss function. So this whole step of moving from inputs from here to the final stage is called as forward propagation. And during the backward propagation, we actually update the weights. As we have seen earlier, the weights are randomly initialized in the beginning, and these weights will be updated using the 4 backpropagation algorithms equation. So let us see how this happens. So first we compute the error between the A2, which is the predicted output, and Y, which is the actual output. Once we obtain this error, we use this update equation to compute the error for the first layer, where we are not discussing this complete derivation, but we use the same idea of chain rule and compute the gradients and obtain this update equation to compute the errors. And to obtain the final gradient, we do delta 2 multiplied by A1 transpose, and the same way we also in the same way we compute gradient for B2 and gradient for W1 and gradient for B1. So these are the parameters: weights of the second layer, weights of the first layer, bias of the second layer, and bias of the first layer. Once we obtain the gradient, we use the gradient descent algorithm, where we try to obtain the new weights using the old weights minus eta into the gradient. This eta is a learning rate. By adjusting this eta, we can make the learning process faster or quicker, but they have both pros and cons, and it has to be carefully heuristically chosen so that we get the proper output. So this is for a 2-layer case, how we obtain the update equations. 2 layers in the sense the hidden and the output layer. Let us now see first an example as to solve this problem, and later see how these update equations, backpropagation equations, can be derivable for the more general case of neural network. So let us take this example where we have some random weights as an inputs and by random biases. So let's solve how forward propagation and backward propagation happens for this case. So as you can see here, the inputs are 1 0 and the outputs is also 1 0. We are supposed to learn the optimal weights and biases which can understand this relation. So if you start with the weight matrix, this is the W1 and B1, this is W2 and B2. We compute the pre-activations of the first layer and post-activations of the first layer, pre-activations of the second layer, and post-activations of the second layer. We have seen already how to do the matrix multiplication to obtain it and pass through the activation function to obtain the post activations. So we can compute the loss function. Once we obtain the predicted output and the actual output, we obtain this loss function, compute the delta 2, which is A2 minus Y, and delta B2, which is delta 2, and also delta 1 by using delta 2 and the weight matrices. And finally we obtain delta W2 using this delta 2 and A1 transpose, and also delta 1 gradient with respect to weights of the first layer and gradients with respect to the biases of the first layer. So in this way we obtain the gradients, and once we substitute this in the weight equations, so we substitute this gradient and obtain the new weights. In the same way we can substitute the gradient with respect to W1 and obtain the new weights. So same thing goes for B2 and also B1. We update the gradients and obtain the values for B2 and B1. So in this way we compute the weights and biases after one stage of backpropagation. We do this kind of backpropagation for multiple epochs or multiple times until we minimize the error, and thereby we say that during the training stage the model got trained. During the testing stage we can pass through the test input to the trained model parameters to get the appropriate probabilities to make a classification. So this is how it works for this problem. Now let us see how we can derive backpropagation equations for the most general case of the neural network. These are the pre-activations, and once we represent in the form of matrix, this is what we get it. and where Z1 is the pre-activations of the ZL is the pre-activations of the Lth layer, WL are the weights of the Lth layer, ZL minus 1 are the L minus 1 of the actually this is AL minus 1. So AL minus 1 is the post activations of the previous layer, and BL is the biases of the previous layer. So once, so let me adjust this. So AL minus 1 are the post activations of the previous layer, and BL are the biases of the Lth layer. So in this way we obtain the pre-activations of the next layers. So as you know, the Z1 Z2 for the initial layer, 0th layer, is actually the inputs. These inputs acts like the for the first layer. Okay, so now let us see back propagation equations. They are exactly similar as how we have seen for a 2x2x2 neural network. First we compute the Lth layer's error, and from there we can compute the from L plus 1 we can compute Lth layer. So when you substitute L minus 1, this becomes the Lth error. From there we can obtain the L minus 1th layer's error term by using the appropriate weights. So these are the gradients for the WL, and also gradient for biases. So we can compute in this. Once we obtain the gradients, we can update using these update equations. WL new value can be obtained by adjusting the old value with and negatively adding the gradients, and also a learning factor which is heuristically chosen. So in the same way we also update the biases. As you can see, we follow this notation where capital letter indicates that matrix, and a small letter and bold indicates a vector, whereas this is a scalar. So in this way we update the weights and biases of a neural networks. Let us discuss how neural network can be implemented without using libraries from the scratch in Python. So as you can see here, we are importing NumPy library. We are not importing any neural networks library like TensorFlow, PyTorch or Keras. And we return a function for computing the sigmoid activation function, and it's also derivative where we compute a into 1 minus a. We initialized weights with random values, and we are using a network where our input is of dimension 10 cross 1, and we are adding random noise to make it 100 samples. So the same input with a little bit of noise has been added, and also the second input which is a column vector where we add once again random noise and make it 100 samples. So we have 200 columns which came from these two vectors, and corresponding, and we concatenate them and make one input matrix X. And we also give, since it's a supervised learning, we also give the corresponding outputs. So if you see here, the outputs of Y are for the first 100 inputs we will be having 1 and 0 as the column vector. For the rest of the 100 inputs we will be having 0 and 1 as the output. So we give this output during the supervised during the learning of the neural networks. So this is the learning rate we are using. It's adjustable, and we can use different heuristic values for either speeding up the learning or to slow down the learning process. So as you can see here, we are using 300 iterations. So we run the same data for 300 iterations so that we get the model parameters, trained model parameters. So as we saw earlier, we take the input vector and the output vector, both are being given to the network to do the so we do the forward propagation first, where our randomly initialized weights get multiplied with the inputs to get the pre-activation and pass through the activation function to get the post activation of the first layer. And in the second layer, the post activations of the first layer acts as an input. They multiply with the random initialized weights to obtain the pre-activations of the second layer, and they pass with the activation function to obtain the post activations. So in this way we do the forward propagation, and for the backward propagation we use delta 2 and delta 1 to compute the error terms for the second and first layer, and obtain the gradients dw2 and dw1 by you multiplying this delta 2 with the a1 transpose and X transpose. So once we obtain the gradients using the gradient descent update rule, where W2 new is equal to W2 old minus learning rate into the gradients with respect to the weights. So in this way we update the weights. So what we have done is we have been checking for the final output for the final input. So we are checking the output of the final input where our network is supposed to learn 0 and 1. So when we run it for every particular epoch, what we got is displayed here. So first let us see how it was before training. So these are the outputs: 1 0 for the first 100 samples, and we have also used 0 1 for the last 100 inputs. These are the outputs, and these values are for each epoch. For the last input we are supposed to get 0 1 as the output in ideal case, but we started with these outputs because we have initialized weights with the random values, and slowly once the number of epochs increases it tends to reach to 0 and 1. So finally at 300 iterations, what we can see here is it has almost reached close to 0 and 1, and finally we got these are the final prediction. So in this way, by increasing the number of epochs, we can train the neural network and establish obtain the trained model parameters to understand the nonlinear relationship between the input and output. Neural networks can learn any function, any kind of nonlinear relation between input and output. So this is how neural networks can be implemented without using any libraries like TensorFlow or PyTorch. In later videos, we will also see how we can implement neural networks using TensorFlow. Thank you.